Hey everyone, and welcome to our lecture on setting ownership and permissions. So in this lecture, we're going to talk about how we can set ownership on files and directories. We'll also talk about how we can set and modify the permissions on those files. And then we'll wrap up talking about special permission bits and various file features. So let's get started by talking about ownership. So every file or directory has an owner and a group owner. And we've sort of alluded to that in some of the previous lectures. We know the owner is the user account or the UID that's associated with the file, and the group is the group name or the GID that's associated with that file. So who can change the owner and the group on these specific files and directories? Well, the root user can for sure, because the root user can do just about anything they want on the operating system. And as a regular unprivileged user, the file owner themselves can change the group providing that they are a member of that new group. So let's look at how we can change ownership in the file manager via the GUI. So typically when we right click on a file, we can go to properties and it'll bring up a window similar to this, and we can see there's permissions on this, and we can drop down and look at different owners that we could set and the access permissions for the owner. Same thing here with the group, and we could drop that down. As a matter of fact, let's just jump over and take a look at an example of this. Alright, so in here in my home directory I have an example.file that we created previously, and if I right click on that and go to properties, in here I had the basic information, so when it was last accessed, when it was modified, the location, the size, this happens to be an empty file, and the file type. What we're interested in here are the permissions. So if we look at this, we see that I am the owner. You'll notice that I cannot change who the owner is because I'm not root. I can, however, change the access, and I can change this to read only, or I can give myself read and write permissions. Okay, so these permissions restrict what we're able to do with the file. If all we can do is read, then I can open that file, but I'm not allowed to save to it. Same thing here with the group. My user account is a member of all of these groups, so I could change to any one of them. All right, we'll leave it as my own group for now. And the access that's provided to all the group members are specified here. So they can be none, read only, or read and write. Lastly, there's this notion of others, and that's anyone who's not in this group and not myself. So anyone else on the system. I can give them read-only rights, I can give them rights to read and write, or I could give them no rights at all and say they can't even look at the file. Lastly, there's this execute bit, and we can turn this on if the file is meant to be executed. So if it's a file script, like a bash script, or if it's a binary file that we can just run, then we would set the execute bit. But this is just a simple text file, so there's no need for that here. Alright, so switching this to read only, let me just demonstrate that now if I go to open the file, we'll see up at the top it lets me know that it's read only, and if I try to make any changes to this, it tells me that it's read only and I'm unable to replace it. Great, so that is a security feature there. So we can come back in here and we can switch this back to read write for myself. And now I can get into this file and I can come up here and save that no problem. Awesome. So one of the things that we're interested in is how can we do this via the command line? So there's a few different moving parts here that we were doing in that GUI. We were changing ownership and we were also changing permissions. So let's look at changing ownership first. So we'll do that here with the chown command. So chown is short for change ownership. And it has a very simple syntax. The first argument that's passed to chown would be the new user that you would like to have be the owner. The second argument is the file that you want to change the owner on. Now additionally, there's some other ways that we could call chown. So you'll see this syntax here with a username colon group followed by the file. So this changes not only the owner, the user owner, but it also changes the group ownership permissions as well. And then lastly, if all we wanted to do is just change the group ownership permissions and leave the actual owner alone, we could leave the owner part blank and just have a colon followed by the group name and ultimately the file that we want to change ownership on for the group. So let's take a look at an example of using this over in the VM. And one thing I want to point out is, again, what our shell prompt looks like. If you remember back, the pound sign means that we're logged in as root, or we're running this command as root, and the dollar sign means that we're running it as an unprivileged user. So remembering back to our GUI example, we can't change the owner as an unprivileged user, which is why if we're changing ownership on the file, we need to be root. But if we want to change the group, we can do that just fine as an unprivileged user. Alright, so let's, jump over here. Oh, let me clear that out. Okay, so we were looking at this example.file, and we see that I am the owner, and my group is the group owner. And let's say I want to change this to the pseudo group, because that is one of the groups that I'm a member of. We can see here. And that's also one of the things that I can do as an unprivileged user. So to do that, we'll do chown, and we can't specify a new owner, but we can specify a new group. So we'll do that with a colon followed by the group name and then the file that we'd like to change the ownership on. Now, if I come in here and list this out, we see that the group ownership has changed. Okay, so next I want to change the actual owner to a different account like George. And to do that, I'd have to either log in as root or preface the command with sudo. And since I'm in the sudoers file or the sudo group, I can go ahead and do that. So let's sudo chown George example.file. So it's going to ask me for my password. Awesome. And if we look at that, we see that that has changed. So one more example, let's set it back to Corey and Corey. So we'll have to do that as root sudo chown Corey colon Corey example.file. So clear that out, and we see that we're set back here where me is the user and my group is the group owner. Great. Okay, so there is another way that we can change group ownership if we don't want to use this colon notion here with the chown command. We can explicitly use the chgroup command, and that changes the group ownership of a file. So just real quick, let's look at that. Chgroup, and we'll switch it back to sudo for example.file, and that works just the same. So it's just the same as saying something like this with the chown command, and that should have set it back. Great, so it doesn't matter which one you use, either one of those is fine. Alright, so next let's talk a little bit about the permission string that we see when we run the long listing of the ls command. So what we see are, here in the very beginning is our permissions, And the rest of this, we've sort of already talked about this, but this is the number of links to the file. This is the username who owns the file, the group who owns the file size in bytes. We have a timestamp of when the file was last modified, and then of course the file name. So what we're interested the most right now is this first part, which are known as the permissions or the symbolic permissions, because we have symbols like R, W, and X to represent what the permission actually is. And these are fairly straightforward. R is for read, W is for write, X is for execute, and if you don't have that permission, then there will be a dash there. And the permission string is broken down into 4 different parts. So this first part is the file type code. And we'll look at a couple of different examples of what can be a valid file type code. But the two that we'll see the most is a dash, which is for a regular file, or a D, which is for a directory. The next 3 characters are for the owner permission. So if the owner has read access, then the R will be set. If the owner has write access, the write will be set. Same thing here for execute. If the owner does not have one of these permissions, then there'll be a dash populated in here instead of the character. For instance, something like this where the group has read permissions and execute permissions but does not have write permissions. And then the world permissions is what corresponds back to this other field. So this is everyone else who's not in a group that's listed. So not in whatever group that owns this and is not the owner would be everyone else. So everyone else in this case has read access and execute access. So expanding a little bit on those file type codes, I said that dash and D were going to be the two that we see the most, but we may also run into like L for symbolic links, or P for name pipes, S for sockets, B for block devices, and C for character devices. So you're probably really only going to see these in the /dev folder. You may see these name pipes and sockets in other places, and symbolic links obviously wherever you have a symbolic link created that's pointing to another file. Okay. Now, talking a little bit more about these permission strings, I had mentioned that these were symbolic permission strings. Well, these symbolic permissions map back to an octal code. So there's 2 different ways that we can change permissions, and we can express ourselves either in this octal code or with these symbolic permissions. Okay, so looking at this, you'll see that the octal code is broken down into 3 digits. Each digit represents one of the groups. So the first digit here, starting on the left and moving right, is for the owner. So the octal code of 7. And the middle one is for the group. And then the last one is for others, or the world. And let's see. Let me bring up something like OneNote here. Oh, and we'll create a new page. Actually, let me just switch this over here. So we'll do a new section. Awesome. So when we think about these symbolic permission strings, let's see, let me go to draw here and we'll move this over to pen. Awesome. So we have this read, write, execute, and let's say that that is for the owner here. Each one of these maps to a bit, so if read is set, then the bit will be 1. If W is set, then the bit is 1. And if X is set, the bit is 1. And in binary, we know that the number 111 maps to the octal value 7. Okay. It also maps to the base 10 value 7. Those are going to be the same up until 7 with the octal values as well. So that's a pretty easy mapping for us to understand. If we look at something like let's look at the group permissions of read, nothing, execute. Then this maps to a 1, nothing is a 0, and that's a 1. So what is this in binary? Well, that's 1 plus, not 2, 4, so that's 5. Mapping back to the octal number from the binary number. And then lastly here, let's look at another example where we maybe have the world or others or just read. So if it's just read, it's just going to be a 1 here, 0, 0. So these guys map down to that, 1, 0, 0. Converting this back into base 10 or octal, we know that this is the 1's position, that's the 2's position, and the 4's position. Only the 4 is set, so 1, 0, 0 maps to 4. Okay, so with that, we could come up with our own permission strings here, and we can see some examples of the different various permission strings and start to understand where these numbers are coming from. So for instance, the world here is dash dash dash. That's obviously going to equate to 0. And the group here is read dash execute. Well, we know that that equates to 101, which maps back to 5, which is why we see a 5 here. And the owner, RWX, maps to 111, which is 7 in octal. Okay, so there is a method behind the madness here. And one more example that we didn't cover is this RWX. So if we have RW dash, if we have that, then we have the 1's bit set here, here, and 0 there, and this equates to 6. So read write access only is 6, and that's what we see here with the read write, read write, read write. 6, 6, 6. All right. So as an exercise, what I'd like for you to do is take some of these permission strings and make sure that you can convert them over to octal like we did over here in OneNote. And then also make sure that you can convert backwards from the octal code to the symbolic permission string. So you can take something like 400 and figure out that that's just read for the user and no permissions for the group or for the world. So how do we set these permissions in the shell? Well, we can use a simple command called chmod, which stands for change mode. So mode is synonymous with permissions. So in this case, we're changing the mode on report.txt to 644, and we should be able to jump back and find that in here. 644 should be read write, read, read. So we can verify this by, oops, where's my VM? There we go. Jumping over into Ubuntu. Let's look at our example.file, and we can see right now it's read write, read, nothing. So let's see if we can chmod this to 644 for example.file. And then when we do our long listing again, we see now that read access has been added in for the world. I think the next example was 777, which would give read write and execute to everyone. Okay, and we can see that there as well. So those octal codes we just learned about, we can use those with the chmod command. And of course we can also use those symbolic permissions that we learned about as well. So here in this case, A stands for all or everyone. So A plus X is going to add the execute bit to everyone. So we can see initially we have RW, RR, and then after we run this command, we'll have the execute bit in each group. Okay. We can also explicitly set our groups to different things. So user and group, or what U and G stand for, equals RW. So in this case, originally we were just read for the user and nothing for the group or others. After we run this command, will be read write and read write for the user and group. This one removes RWX from other. Okay, so if we see the original permission string, the other group had read and execute permissions. After we run this, they do not have any permissions. And we can also specify multiple symbolic permissions at the same time if we separate them with a comma. So in this case, the group is going to lose write access and others are going to lose read and write access. So what was originally this permission string will become this one. So when it comes to the chmod command, you can go either way. You can either use these octal values or you can use these symbolic values. Next thing I want to talk about is the umask. So the umask is used when we first create a file or a directory. So the default permissions on a file are 666, which we saw previous as read write, read write, read write. So by default, when we create a file, everybody can read and write to it. And by default, when we create a directory, everybody can read, write, and execute that directory. So the execute bit's what lets us actually change into a directory. So that's why that's important and different than when we create a file. Okay, so coming back here, directories by default are 777. Now we have this notion of a umask that is removed from the default. So the umask is set usually in our profile, and we can see what it is by just typing umask and pressing enter, and we see that it's 2. So 2 would be subtracted from either 666 or 777 depending on if we're creating a file or a directory. And we can change the umask as well by just specifying a number to the umask command. That would change it just for our session. If we wanted to change it a little bit more permanent, we would put that in our startup script. Okay, so let's come over here and let's look at if our umask is 2. If I create a file called, let's see, umask example, let's look at the permission string for it. Let's see, umask example. We see that it's RW, RW, R. So originally we know that it would be RW, 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 and we are subtracting our umask from it, which again is 2. So if we subtract 2 from, what is this, 666, we get 664, which is what we see here. Now the root user's umask is always, or typically, 22 by default. So if we change our umask to 22 and we go to create a file, so let's touch umask example 2 and let's ls out both of them. We can see the difference here is that by default root does not give write permissions on files to anyone else in their group, just the read permissions. Alright, same example here. Let's look at creating a directory. So if I make dir test1, and if we look at the permissions on test1, we see that they are missing the write and the write here because we subtracted 22 from 777. So that should be, if we take 777 minus 22, it would be 755. And that's what we're seeing here. 7 for 111, 5 for 101, 5, 101. Okay, same example, let's set our umask back to 2 and create a directory, test2, and we see that everybody has read, write, execute except for the others don't have write abilities. Okay, so we really only change this when we want to change what the default behavior is when a file or directory is created. For the most part, we're usually fine with leaving that at 2 or 22 for the respective accounts. So now let's talk a little bit about some special permission bits and file features. The first one I want to talk about is the sticky bit. So the sticky bit can be set on a directory, and what it allows is for any files or subdirectories created inside that directory that the sticky bit is set on can only be deleted by the owner of the file or by the owner of the directory. So the way that we set the sticky bit is with chmod. We've been doing just 3-digit permission strings. Well, there is this 4th digit that we can use to specify some of these special permission bits that we're learning about right now. So the first one is a 1, and that sets the sticky bit on this public directory. And as we saw before, there's symbolic ways of doing that as well. So other plus T sets the sticky bit on the public directory if we want to do it symbolically. But before we can really understand why we need the sticky bit, we need to understand what the problem is. So to illustrate this, let's take a look at an example in the virtual machine. So we are already familiar with the temp directory in that it contains temporary files that are created by users or programs on the system and can be accessed usually just for the duration of that particular uh, uptime or from the last time that the computer was rebooted. So typically when we reboot, what's in /temp goes away, and then when we come back up we have a fresh /temp that we can put things in. So we don't store things persistently in here. What I want to show you is, let me clear that. I meant to do a long listing on temp here, and you can see that there are different owners in this folder. Okay, and the idea is that I shouldn't be able to delete something that belongs to root, right? Because those are root's files and root created them and conceivably needs them in order to keep running their program. So let's create a similar sort of structure here. I'm going to create a different temp directory. So let's do a sudo make dir /temp, and then let's relax the permissions a little bit. So 777 on /temp. That way everybody can get in here and read and write to this particular directory. So the first thing I'm going to do is I'm going to create a file in here. So /temp Corey's, I won't call it secret, let's call it important file. Okay, so if we go to /temp and we look, we see my important file is there. Let's actually also look at that, the long listing, and we can see that I can read and write to it, my group can read and write to it, but everyone else cannot. Okay, everyone else can read it, but they can't write to it. Now let's open up a different terminal and let's log in as George. So I'm going to switch user over to George, put in his password. George can change to the temp directory, and he sees my file there. Now, if George wants to read the file, he can do that. We see that it's read-only, so he can't make any changes to the file here. The system won't let him. But what if George tried to remove my file? So there's a little safeguard here, and it's saying, are you sure you want to remove this write protected file? And say, yeah, sure, that's fine. Well, look, George was able to delete my super important file here. And that's not something that we probably intended for George to be able to do, because George didn't even have write access to the file. So why is it that without write access, George was still able to delete my file? And the answer to that question has to do with the permissions on the directory. So /temp, remember everything in Linux is just a file, so this directory is just a file that contains contents of what's inside the directory, and the other group has the ability to read and write the directory, so therefore the other group also has the ability to delete files out of that directory as well. Now if we want to prevent something like that from happening, then we would set the sticky bit. So let's see, chmod 1777/temp, and I need to do that as sudo. So we'll run that again. And now let's do an ls on it. And we see that there is a T now in this other group. Now, that doesn't necessarily only pertain to others. It just means that the sticky bit is set on this particular directory. Okay, so let's clear our terminals here. And let's go through the example one more time with the sticky bit. So I'm inside the temp directory. I'm going to create Corey's important file. And then over here, George is going to see my important file. He's going to know that he doesn't have write access. And if George is feeling a little malicious, he may try to remove my important file. But now the operation's not permitted. So that in a nutshell is exactly why we need to have the sticky bit, is so when users are sharing a directory, they can't delete each other's files, because they need the permission to read and write to that directory, to read and create files and execute to get into that directory and search through the files, but they don't need permission to be able to delete other people's files. And going back to our example of /tmp, let's just investigate, well, what are the permissions on it? And what you'll notice is the sticky bit is set on the temp directory. So that's sort of our classical example of why we need the sticky bit. Okay, and we didn't do the example with the symbolic code, but where I did the chmod 1777 on /temp, we could have done O plus T and everything would have worked out the exact same. Okay, and that's just saying that, yeah, we'll see that in the world permissions down there. So the next special bit is the set user ID bit, or the SUID bit. And what this does is it runs the program with the file owner's permission. So there are a couple of different programs that do this, and we'll take a look at an example of some of them. The way that we can set this SUID bit is by using 4 in that fourth digit's place, or by using the +S on the symbolic code for you or for the user. So user +S will set the SUID bit and run a file as the owner. So why would we even need to do this? Well, let's come over here. We can close out of our other terminal. And let's figure out where's the password file. The password program is here. So if we look at a long listing of that, what you'll notice is that the owner has this S where the execute would be, and that's what signifies to us that the SUID bit is set. So whenever we run the password program, it's actually running it as the owner, which is root. Okay, one way that we can illustrate this is with the whoami command. So which whoami is in user bin whoami. Okay, copy that. Let's look at the permissions. Oops. And we see that it's owned by root, group is root, and it's just got regular permissions, no SUID bit set here. Okay, and if I run whoami, it says that I'm Corey. Now, if I chmod this to 4 and what would this be? 755. It's 755. This whoami command. Of course, I can't do it. I need to be root, so we'll run that with sudo. Okay, let's clear that, and then let's go back and list out the permissions again, and now we see that the SUID bit is set. So it should run this command as root, and the whole purpose of this command is to tell us who we are. So what I wanted to illustrate here was when we run this now, it thinks I'm root because it's running this program as root. So there's certain programs that we have to do this for, and it just depends. It's a way to delegate access to a command with certain privileges. But you do have to really trust that command, because once you do that, whoever runs it is running that program in the context of either yourself if you were the owner, or root if root is the owner, as in this case. So what I'm going to do is I'm going to go back and I'm going to remove that, and I'll remove it symbolically just so that we can see an example of that. So chmod, the user -s, user bin who am I, and then let's ls that, and we see now it's been set back, and this is an X instead of an S now. So who am I tells me I'm Corey now. Alright, and just to sort of circle back around to that passwd command, the passwd command has to become root in order to work because it modifies that etc shadow file. And if we look at the permissions for etc shadow, we see that only the owner, or root, can write to it, and only the shadow group can read from it, and of course root can as well. Alright, we have the same notion if we need to run a program as a particular group. In that case, we would just do a 2 instead of a 4, and this would set the sticky bit on the group. Okay, so real quick, we'll look at an example of that. Let's just change the group of the who am I command. So sudo chmod 2 755 user bin who am I, and then if we look at the lawn listing, we see that the SUID bit is set here for the group now. Now I don't have a good example that's going to show us like the who am I command did, showing us running as root. But if we needed a command to run under the context with the group, we could do that with this SUID bit. And again, let's just go ahead and remove that. So in this case, it would be group -s user bin who am I, and we can see now that it's set back to an X instead of an S. Okay, additionally, there is a way that we can hide files. So we have all of these hidden files that are called dot files, and we call them dot files because they start with a dot. So it's kind of a naming convention, and if a file starts with a dot, by default it's not going to display to us either in a file explorer or in the ls command. In Windows, we call these hidden files as well, and there's a hidden bit on Windows, and you can go in and modify that so that your folders will show you the hidden files. But on Linux, if we want to see them, we can do the same in the GUI, or we could do this ls-a that'll show us all the files. So let's take a look at this in the VM as well. If we come over here and I'm in my home directory, so if I do an ls, I can see all of the files and directories, although not really all of them, because if we do the -a, we will also see the hidden files. So these hidden files, they're typically configuration files. They store settings. Different programs have them, maybe for bookmarks and stuff like that. One good example is .ssh, has our user SSH config, and any public and private keys usually go in there. We got the .bash history, which has a history of the commands that we ran. As a matter of fact, when we run the history command, this is where it comes from. And .bashrc is one of those startup scripts that gets loaded when we first load up bash. So if we wanted to, for instance, change our umask or something, we could do that in the bashrc file. So lastly, just how do we view directories? You may have noticed with the ls command, if you specify a directory name, it doesn't show you that directory. Instead, what it shows you is the contents of the directory. So for example, let's take a look at, well, there's test one. Let's go into test one. There isn't anything, so let me touch X and touch Y, and then we'll come out. And if I do an ls test one, it actually shows me the contents of test one. But if we were more interested in looking at test one itself, we could pass in -d, and that will show me the directory test one, and we see that. And I usually like to use this with the long listing so that we can see like the permission strings on a particular directory. Alright, so that wraps it up for this particular lecture. Uh, if you have any questions, please feel free to reach out to me. If not, I hope you guys enjoy the exercises, and I'll talk to you all in the next video. Thank you.